So we can use substitution for exponential forms as well. Essentially, any kind of integral that has an inside function and outside function, you will be able to use substitution. Now for exponentials, it's a little bit harder to notice this as an inside. The inside is really the exponent. And so when I am integrating e to the u, I'm going to be looking to make sure my du dx is there, my derivative of u, and then my antiderivative will just be e to the u plus c. If my base is anything other than e, I will just have to divide by natural log of the base, as we did before with our integrals. So number 5a, we have e to the 3x plus 1 dx. Whenever I have an exponential, my u is the exponent. My u is 3x plus 1. Sorry, I should say if I just have an exponential. Sometimes you might have a more complex equation where your u is actually the exponential itself, but we'll get to some of those. So here my derivative of that is just 3 dx. I don't have the 3, so I'll need to balance like we have before. So I will have 1/3 times the integral of e to the u du. The antiderivative of e to the u is just e to the u. And then when I replace my u, it's just e to the 3x plus 1 plus a constant. In part B, we have 5x e to the negative x squared dx. Again, I'm going to make my u that exponent, the negative x squared. Because then if I take the derivative, I get negative 2x dx. And while that's not exactly the same thing as what I have there, I do have an x dx. And so I know I can balance this with a constant. So as long as those powers match up, I'm good to go. I will need to divide by negative 2. And I can multiply by 5 or factor the 5 out in front. So I'll have negative 5 halves e to the u du. So my antiderivative is negative 5 halves e to the u plus c, which gives me negative 5 halves e to the negative x squared plus c. In part C, we have the integral of e to the 1 over x squared dx. It might be helpful for you to think of this as e to the 1 over x times 1 over x squared dx. Think of it as the two separate parts. But again, a lot of times your starting place for u substitution here is to pay attention to what your exponent is, your variable exponent, that 1 over x. So let's say our u is 1 over x, which remember is x to the negative first. The derivative of that would be negative x to the negative second dx. That is this 1 over x squared, except it's not negative, so I'll need to balance. Negative du is equal to 1 over x squared dx. That's this part right here, or the x squared dx. And so then I have the negative integral of e to the u plus c. The antiderivative of e, sorry, I forgot my du. E to the u, I'm getting carried away. This is just e to the du. I don't need my plus c yet. E to the u du. Then I'll have the antiderivative is negative e to the u plus c. And then I can replace the u with the 1 over x. So it's negative e to the 1 over x plus c. In part D, I have the integral of sine of x e to the cosine x dx. My u again will be my exponent, cosine x. My du, derivative of cosine x, is negative sine x dx. I just need to balance with my negative, so I'm going to have negative integral of just e to the u du. And so my antiderivative of that is again negative e to the u plus c. And so my final answer is negative e to the cosine x plus c. And finally, we can also apply substitution for 1 over u forms. So remember that the antiderivative of 1 over u is natural log of absolute value of u plus c. What that's going to look like for u substitution is you're going to have a derivative on top, so u prime over your function on the bottom. And so you'll notice a lot of times your degree on the top is 1 less than the degree on the bottom, or you'll just notice a derivative function on the top compared to the bottom. So let's check out A. We have the integral of 6x minus 2 over 3x squared minus 2x dx. So I recognize that the degree on the bottom is lower. That's a good sign that that's going to be my u. So let's see this as u equals 3x squared minus 2x. if I take my derivative, I would get 6x minus 2 dx. Now that does match up exactly with what I have in my numerator. So that works out nicely. Otherwise, I might just, again, be different by a factor. I would have to factor it out of that whole thing, the whole 6x minus 2. When I rewrite this, then this becomes the integral of 1 over u du, because I had that even exchange there for my du's. Now you can write this as u to the negative 1, but remember you are not using the power rule here. 1 over u has the special rule for the natural log. So my antiderivative is natural log absolute value of u plus c, or natural log absolute value of 3x squared minus 2x plus c. In part B, we have the integral of secant squared x over tangent x dx. So here you might see the degree is higher on the top, but don't get confused there. You really want to be thinking which one is the derivative of which. And again, secant squared is the derivative of tangent. So I'm going to be making my u the function on the bottom. And my derivative of u is secant squared x dx. So notice I have that on the top. Just a hint, you'll never be dividing by your du. You always want to multiply by your du, so it itself will not be in the denominator. Like you won't divide by du. So this is du over u. So notice the du is in the numerator, not in the denominator. The antiderivative of that, sorry, I could have written that as 1 over u du as well. It's the same idea. Is natural log absolute value of u plus c. So natural log absolute value of tangent x plus c.